And thanks, Terry, for inviting me. And also, when Terry invited me, I said, can we bring some people from our centre to come? And there's quite a few of them here. So hopefully there'll be some centre intermingling during the next 2 days between the Decision Science and the Coral Reef Study Centre. And that's been good. And thanks, Jenny, also, and all the others who've organised these 2 days. It's great also to see some of the ARC people here as well. They probably don't often get out and much time to come and listen to a few talk from centres of excellence, so that's good that they have got that sort of time. What am I going to talk about? Our centre is all about, it's not really in some senses a science centre. Don't tell anybody that, Nathan. In some senses we call it decision science, but decision science isn't a science. It's not a theory. It's just a tool, it's an approach, it's how you solve problems, it's an approach to solving problems. And I think there's a lot of confusion about what decision science is or decision tools are. And I'm going to try and hope to clarify that a little bit and make it a little bit less mystifying. It's not lots and lots of maths. Decision support is if you're a Roman army and an eagle flies past on the left-hand side, you send the cavalry in first. That's decision support. It's not very good decision support. It may have worked once or twice and it may really be fairly random. And to be honest, I look at a lot of the decision support we do in the environment in Australia and it's not much better than that. And I look at a lot of the decision support that we see for the Great Barrier Reef and I'm not that happy. So that's what this talk is all about. But the real person who should be attacking, because I'm going to attack you and you'll have to attack me back, is Carissa, who's here. And she'll be talking tomorrow and she's largely responsible for a lot of this thinking and this work. Just to release an example of where to go and where we're getting with decision support tools. So generally, I'm going to basically try and make it clear that there are lots of ways you can support decisions and a lot of them really are confusing, misleading and bad. The biggest problem is quite clear. People fail to prioritise actions. We see maps of threats and we say that is decision support. We see maps of hotspots of endemic species and we're told that is where you should act. Well, it's not. They're wrong. If you don't include actions, if you don't decide what actions you're taking, like make a marine park, change the way land is managed, change runoff, remove, put on turtle exclusion devices on boats, if you don't have an action, you are not doing decision support. All those maps, those threat maps, those endemic maps, all those maps are not decision support until you've got an action. So don't tell me they are. And that is the commonplace situation that scientists do. And the trouble is with actions is you actually have to think about feasibilities and costs, and we don't like talking about that, so I'm going to talk about that. Decision science doesn't have to involve making huge, complicated economic models, and that doesn't have to involve turning nature into money. And I'm going to show you a very simple approach to decision support that almost solves 95% of your common problems and is explicable to anybody, and it's called shopping. Okay, I don't do it, I gather people do. 5 billion people do it pretty well every day. I try and avoid it. Cost effectiveness is a way of determining which actions to take to save environmental assets. It's the benefit of the action divided by the cost of the action, and it's no more than being able to divide and multiply. If you can divide and multiply, you can do this. If you can shop, you can do this. The approach is called structured decision making. We've been doing it for a long time. I didn't even know it was called structured decision making, but of course the Americans did it 10 years before we did, as they always do, and there's book after book about how to do these things. It's just that we don't get trained as biologists in structured decision making. It's a well-known process, and the process is really just this. Come up with some objectives, think of some alternative actions, work out the consequences of those actions. What is that? That's what we think of as modelling. That's just modelling. So working out what's going to happen if you do things, there's consequences in its modelling. And we tend to focus a lot of our attention on that. That's where all the biological data piles into these models. But the whole process is equally important. And really the setting of the objectives is probably one of the most important things, and the choosing of the actions. We tend not to focus on much of that. Because as scientists, we're interested in how do we predict the future and how do we use our knowledge. And then we have to actually enact them, look at the trade-offs and evaluate those issues. So there's a general process. And I think the trouble is with scientists and all of us in a sense is when we're faced with a problem, that's our normal response, is to say we will go and get more data. In fact, I remember Senator Hill saying, Hugh, you're the only scientist who I ever talk to that doesn't say, give me $10 million in 10 years and I'll tell you the answer then. So I just gave bad answers immediately and cheaply. But we can't keep using that excuse that we need more data. And again, yet again, this example show you that we can give good answers now reasonably quickly and reasonably cheaply without just saying we don't know enough. Of course, we'll always have better answers if we do all the science better, and we've got to keep doing that. So when does prioritisation go wrong? This comes from a paper by Eddie Game, and it's recently published. And I really wanted to just highlight 2 or 3 of these things. Many people solve problems where they actually don't have a clear objective. So I'm going to ask, give you a heads up now, what is the objective of the Great Barrier Reef? What is the objective? What is the quantifiable objective? By 2050, what coral cover do you want? 30%? Where do you want it? Do you want it evenly? Are you happy to have 15% coral cover in 2015 with 45% coral cover in the north and none in the bottom 2/3? Is that your objective? Is it written down anywhere? How many dugongs do we want? How much seagrass do we want? How do we know if we've even got a success? Now, if you ran any business without a quantifiable objective and a time plan, your business would go broke and nobody would give you any money. Okay, so the first thing we've got to do is actually decide what we're trying to do. It's very hard to decide what to do until you know where you're going. And the other thing is we need to cost out a lot more of these actions. This is starting to happen better, and there are more and more less things. And the other thing we often do is number 7 was my favourite one, is people often clearly can't divide and multiply. So they look at criteria and issues and they turn them into scores and they add them up, and that's prioritisation. If you ever see somebody adding criteria or ranks or scores and saying they're doing some maths, then you have my permission to strike them. Okay, so we're going to quickly go through a couple of examples, well, maybe just one if I haven't got much time. And the first one is just something very straightforward, is something about prioritising actions for flatback turtles. And this is a project that Carissa did with WWF funding, a short project, just 6 months. And we also looked at sediment control as well in that short period of time. It's based a lot on expert opinion, a lot of people probably in this room who gave us information and data about actions you can take for turtle conservation. NSSA, it's all built on this simple notion that you can take an action and you can work out whether it's a good one or not by dividing the benefit by the cost. Now, the cost I'm going to talk a bit about. What's the benefit of an action for turtles? And we turn that into basically a scaled growth rate, If it was sediment, it might be how much sediment does not go out of the end of the Fitzroy River if I take this action. Okay. So that's all you need to do. And you can rank all your projects by cost effectiveness and you can decide which one's best to do. And we aren't the first people to think for this, and this is a very good way of showing how to visualise these cost effectiveness of these actions. And this is taken from Climate Works, and these are the people who are trying to work out how should we get CO2 out of the atmosphere, how can we reduce greenhouse gas equivalents in the atmosphere. So actually each one of those boxes there is a project. It's a project. And the cost effectiveness is the y-axis, and the ones that are high are very ineffective. They have a high cost per unit benefit, so it's the reverse of cost effectiveness. And the amount that you get out of the project is the distance along the x-axis, it's the benefit. So the ones on the left, this is for carbon, this is stolen for climate work, they are activities that reduce a certain amount of carbon going to the atmosphere, that's the movement to the right, and they're actually not only they're negatively cost effective, that means they make us money. Generally in the environment we don't have them. The ones on the right are the ones we're interested in, and they're scaled from the most cost effective to the least cost effective way on the right. And they're basically saying it costs you a lot of dollars per unit carbon. So if you can look at these projects like that and you say, right, I'm just going to spend all my money until I move away across until I've run out of money. So I'm spending money till I run out of money. Or if you want to meet a certain target, then you have to get there. And you would choose the most cost-effective ones. The ones on the left are things like low-energy light bulbs. The ones on the right might be carbon sequestration. So that's how cost-effectiveness works, and it can be put in a particular diagram, and you can evaluate all your actions in a simple way. So we'll try and do that for flatback turtles very quickly. And we just chose this because it was convenient, and we had people like Cole Limpus and Milani and Mark and others to help us work out what actions we could take, and we looked at particularly around the Fitzroy River population of this turtle. The objective, you've got to have a clear objective, and you could think of lots of them. It could be minimise the extinction probability, maximise the numbers. We looked at maximising the replacement rate. So on average, how many female turtles does a female turtle create to adulthood, which is basically like big R, effectively. And we can then use that to evaluate all options. We thought of all these actions. So this all comes out of the mind of experts. We're not running around looking at flatback turtles. We just get the experts in the room, and we did this with the sediments and grill them until they say, these are the things we could possibly do. These are the threats to the species. And if we do these things, then we think that certain aspects of the life history of flatback turtles will be better off. So we've got to cost them all out, and we did, again, a lot of that by expert elicitation, reading documents, Jutta and Carissa going through documents, trying to work out what they all cost. In some senses, now it's getting really boring, this talk. It started boring, it's getting worse, because nobody wants to talk about money. But if you don't do this, you can't give any management advice to anybody. Just, it's our responsibility not just to tell people the benefit actions. If you don't do the cost side, then basically you're really only doing half the job. And it's intriguing when you talk to state and federal agencies, state agencies, about the cost of conservation. They don't know. They have never done it. So many of our things are uncosted. Okay, so I'll give you a couple of examples. One of the things people suggested is, okay, clearly with turtles, one of the problems is light, and these are all the different things we could do to reduce the light pollution that disrupts their life cycle and causes the baby turtles to go the wrong direction. So they're a whole heap of things. They're all going to give us different sort of benefits. They're all going to deliver different sorts of costs. This was one of the most cost-effective actions. This is actually just basically getting rid of ferals that dig up the nest and eat the hatchlings and also eat the eggs. And they've all been, again, costed out over a 20-year project. We looked at sediments as an activity for the turtles. We also looked at restraining coastal development as an activity for turtles, and we looked at things like removing fish licences, so the collisions and the incidental captures, the bycatch would also be reduced, so the adult mortality could be improved. And then also some things that would deal with climate change, like shading the beaches and stuff like that. So in the end, you've got to basically look at all those actions and work out what part of the life history of a turtle do they affect, and if you take the action, how much does the probability of hatchling getting from the beach down to the sea improve? How much is the probability in animal getting from the age of 1 to the age of 30 or 15 so it breeds? What's that improvement? And we've then got to evaluate it in terms of a very simple model. Rather than building a big complicated population viability analysis model, we just said we're going to use this replacement value. So it looks like a horrible formula, but it's just one formula that tells you the benefit of moving any of those parameters. So if you can move any of these parameters, you can immediately tell how much you improve the replacement rate. That means you can evaluate all the actions in the same single currency, increased replacement rate. So you need a benefit function. And you've got to think hard about what that benefit function is. And arguably, one of our other big problems is being indecisive about benefit function. What is the benefit function for the Great Barrier Reef? Are there 10 of them? Are there 3 of them? Is it coral cover? Is it fish diversity? And this is the result. And in fact, when you do it, obviously this is a very short study. I mean, just 2 or 3 months of work with a lot of expert advice, and basically said the predation control and the runoff and the light and the bycatch were relatively cost effective and delivered enormous benefits, whereas restraining development and all those climate change mitigation activities, adaptation activities, were not going to be cost effective for this species in this place at this time. And so that tells you, there's your shopping list. Start at the left, go to the right. If you want to buy as much as you can for a certain amount of money, just keep going to the right. If you want to just get replacement level to a certain state, like 1 or 1.1 or 1.05, then go to that point and then you're happy. So this tells us what to do. We can do this for anything. And we did it for sediments as well, and Carissa did it for sediments and try to minimise the amount of sediments coming out of catchment. What land management activities will minimise the amount of sediment coming out of the Fitzroy River or the Plain River per unit dollar? And I hope that is how we're delivering our management strategies now. But you could do this for dugongs, you can do it for seagrass, you can do it for any coral cover, any particular attribute you like. The key is having a clear benefit function, having a clear cost of actions. There's no complicated decision support tool here. All we're doing is shopping. So it's not complicated and it's not that hard. And all of that's written up on Carissa's website. And she also there talks about some of the other prioritisation methods we know are out there for catchment management, which break at least 5 of our rules of how to do good prioritisation. So if you want to read that and then get angry with Carissa, then go to her website. So I want to briefly end by saying we need very simple models, and I know we can create massive models. Sarah, I'm sure, will create a $10 million model of how the Great Barrier Reef works, and we'll put in every boat and every fish and every ascidian, and we'll run it forever. People never understand those models. The model I just talked about, I know there was a nasty equation in there, but that is all, we're evaluating our actions based on one number. I think we need some simple coral reef models that are stochastic. And people think stochastic models mean you have to go to a simulation, and that's rubbish. There are analytic answers to stochastic model. This is Hugh's coral reef model, the worst model in the world that will offend everybody in the room, that I invented on Fitzroy Island because I got really, really frustrated with people not telling me how their science could be used to evaluate actions. So there it is. There's a coral reef, there's a coral reef cover, there's a threshold, there's a growth rate, a recovery rate, there's a frequency of exposures, and there's a sensitivity, which is how much you'd get knocked down every time there's an exposure event. And that's a stochastic model. I don't actually have to simulate. I can tell you this is the model that insurance companies use to work out their finances. These things going up, are you paying them your monthly rates, and those jumps are cyclones and fires and hurricanes that cause them to lose a lot of money. So the maths of this has been done for 50 years, and roughly speaking, there is one very simple expression for mean coral cover using those three parameters, even though it looks like a complicated stochastic model. And you can also have a simple expression for the probability of going below a threshold. So we could now take any action and evaluate it on this formula. So if I could move R up, or if I could move S down, and it would cost me a certain amount of money with an action, I can just evaluate it according to that formula. And I could evaluate for hundreds of reefs or few reefs. I could build it into a system model. These are the kind of things we need because you can't do it simply enough. It's very hard to convince people to do that. Having changed a lot of policy in Australia, the simple models are the ones that change policy best. So I'll end up asking you some questions that you may not want to answer or not. Okay, so Carissa and Utah did in 6 months for $30,000. I mean, I don't know why they just didn't build a model of the entire Great Barrier Reef and solve every single problem. They had enough time, 6 months. They've actually given us a decision support approach to do pretty well whatever we want to do. But somebody's got to decide what we're trying to do. Somebody's got to take this decision. And I'd like that to happen sooner rather than later. And if you want this amount of coral cover, then where are you happy for it to be? Are you just as happy to have 45% in the north and the bottom 2/3 completely bare? Or would you like to have 50% everywhere? Or would you like to have wonderful coral cover and diversity right next to every tourist resort and you don't care about the rest of the reef? These are decisions we have not made because we never make triage decisions. We never make prioritisation decisions because we're too frightened. But if you can't make these objective decisions, you can't actually do any decision support because you can't calculate the benefit of an action. So everything I've said has been a waste of time. And maybe this gets back to Terry's key point. Governance requires clear objectives and clear processes to make decisions. You actually have to say what you want. So I think that is the summary of my talk. And then I just blindly advertise our centre and say, if you really want to know what we're doing and you want to see it in plain English and you want to talk to people who can make sense, then read Decision Point, which is our magazine. Lots of other people do, like 5,500, and that gives a nice brief summary of all the things we do. And I might say anything that did make sense in this talk was probably done by somebody else. Thank you very much.